just want to come back here. So I have updated my slides here. That will be the unit about conservation of energy. And I'm going to have the test in mind. So I want to make sure you know how to use the conservation of energy. So you're going to say before, so that before will include all potential energy. So it could be gravitational potential energy plus gravitation plus elastic potential energy plus whatever work is done on the system. So that means you are putting energy into the system. So if you push, for example, I'm going to give you an example, but if you apply a force over a distance, that will be work done on the system. So energy is being transferred to the system, and you also have to do minus the work done by friction. So conservation of energy will be the total energy you begin with, potential kinetic, plus whatever is added to the system, minus the work done by air resistance or friction. That will be equals to the energy after. Now, a different way to write exactly the same thing will be the net work done on the system equals to the change in kinetic energy. It's the same thing. It's a different way to write it down. Okay, so instead of writing the conservation of energy this way, instead you can say the net work done on the system equals to the change in kinetic energy. And when it's friction doing work, it's going to be negative. Is that clear? Okay, so I want to make sure this is, I don't have the right glasses. I cannot see anything. I have so many bags. I don't know which one has the right glasses. Okay, that's better. Okay, let's just to make sure you understand, let's take an example. So for example, here, let's say you have like a cart and it's moving, it has an initial speed. Okay, so when you start your stopwatch, okay, it was already moving, and then you come here and you start to push on it. So that means you're gonna apply a force. So there will be apply force, okay? So of course you have to take the x component if you're not pushing parallel to the displacement, but here I want to simplify. And maybe you're going to have some friction. Friction is always along the x-axis, and you go here and you push over a delta x, right? So at the end, when you stop your stopwatch, the thing is going to be here. Let's say you overcome friction, so that means the velocity is going to increase. If you apply force equals to friction, the velocity is not going to increase, which means there is no change in kinetic energy, and that will be at some, see, it's going from here to there, and there is an acceleration. So in that case, you're going to say whatever energy it had before, which is kinetic. Okay. Now, if you happen to be on a slope, okay, remember I have the test number 3 in mind. If you are on the slope, then potential energy is involved. Okay, but not in that case. Plus energy that you add to the system, which will be the force applied times the distance. So that will be energy added to the system. Okay, minus, it's always minus the work done by friction, delta x. So these are called non-conservative force, right? So it's not like a restoring force like gravity or Hooke's law. Will be equals to the final potential, the final kinetic energy. Is that clear? Now you can write exactly the same thing. Okay, you would get the same thing if you say that the net work done by the net force on the cart equals the change in kinetic energy. So this is called the kinetic work theorem, but you will get the same thing. Because what's the net force? What will be the net work will be the net force, which is the force applied minus the friction over delta x equals change in kinetic energy. So I want you to realize that these are the two things. Okay, it's different ways. So of course, conservation of energy can be easier to deal with this one. It depends. Okay, it depends on the situation. Is that clear? Okay. So you can, for example, and again, you have different way to do it, right? So let's say you are on an inclined plane now, okay? Okay, and you are pushing here. And let's say you start from 0. So here there is no speed and you start to push as hard as you can, right? And so that will be your applied force. Of course, here you're going to have kinetic energy, but you also have the weight. Remember that force from the weight will be mg sine. Do you remember that? Yes? And maybe it has some, so maybe initial velocity equals 0. You're going to go up here. You push as hard as you can. You overcome kinetic friction. You overcome the weight. Okay, the weight pulling down slope. Remember, the weight has two components. The one that you have to work against, which is with a sign, and the one that is against the normal force, which is mg cosine. So anyway, so you go there and maybe you're going to increase the final velocity. Okay, it depends if you overcome both of those forces here. Is that clear? So you have two ways to deal with that. If you say conservation of energy, okay, you are only including kinetic energy, potential energy, and the work done by you and the work done by friction. You don't include the work done by gravity because it's included in the potential energy. So I'm going to use that here, okay? So at the beginning, do we have a potential energy? No, because you take potential energy to be 0 here. Okay, so there will be a tricky equation. You want to make sure where is the potential energy equals to 0. You are the one who decide. Once you decide where the potential energy is 0, you have to stick to it. You cannot change. So I decide potential energy equals 0 here. So that will be 0 plus maybe there is no kinetic energy. So that will be 0. So that will be gravitational potential energy plus kinetic energy to begin with. There is none, okay, because it was no velocity here, plus the work done by you on the cart, okay, times the distance. So okay, g, okay, I'm going to call that distance g. Agree? Okay, you have a sign, like if you use sine, for example, equals opposite over hypotenuse, okay, minus the work done by friction times d equals, okay, the kinetic energy after m 0.5 mv squared final. Do we have potential energy at the top? Yes, right? So you have to know how to use the equation potential energy, which is mgh, right? Okay, so that will be if you use conservation of energy. So it's very simple. Mechanical energy before, so potential plus kinetic, plus whatever is being applied to increase the speed, minus the work done by friction or air resistance will be equals to the total mechanical energy after. Is that clear? And you can solve for whatever is to be solved. Okay? Now you can show, so that will be way number 1. way number 2, you can say that the net work, okay, it's not going to be the same thing. The net work done on the card equals the change in kinetic energy. So now you have to be very careful because that will be the net force times the displacement equals the change in kinetic energy. So what will be the net work? Now you look along the displacement, okay? What is the force applied? You're going to have, what are the force applied? Your push. Do you agree? We review for the test and we are reviewing for the final. So it will be the force you're applying, yes? You wake up? Are you awake? So positive work. So what is doing negative work? Friction, very good. So I'm going to do minus. It's stealing energy from you. So the net work is the net force. So I'm looking for the net force. What else is fighting against you? Why do you have to push so hard? Yes, gravity. But which component?
Sine.
The sine, exactly. So when you are going up an inclined plane, you are not working against the weight, the whole weight, only it's going to be diluted. That's why we have inclined plane. That's what the Egyptians are supposed to have been using. So mg sine, and that will be times the displacement, and you're going to find a change in kinetic energy. This one or that one, it's going to be the same thing. It's the same thing. Understand that? Because we're going to have sine alpha equals opposite, which is h over hypotenuse. So h equals sine alpha d. So you massage, you malax, you shake, and you will get the same thing. Okay, you distribute, so up, the apply force times the distance, minus kinetic times the distance, minus mg sine times d equals the change in kinetic energy. And guess what? That's going to be h. And we get exactly the same thing. Yes.
So I don't understand the first part for mode A, like the first,
So the first one works like this. The total amount of mechanical energy you start with, so potential plus kinetic. And then you can add more energy into it if you apply a force, right? So if you apply a force, you're going to push, it's going to move faster than before. Minus energy taken away by friction will be equals to the total amount of energy after. And it's the same thing. So if you think of energy like a container, so it's like a container. It's like some container here, right? So you're going to have some potential energy. So that will be potential energy. And then maybe you're going to have kinetic energy in red. And then you can add some energy here if you apply a force, okay? Or you can also take away energy, so because of heat. Is that clear? But the total amount of energy will stay the same. So it's whatever you begin with, plus energy you pour in your container, minus energy you are taking away. Okay, so mechanical energy, so potential plus kinetic, plus whatever you add, minus whatever you take away, equals the final potential energy. Is that clear? So why do you add? Because if as I've said just before, if it was moving like you're pushing a wagon, it's moving. If you push, it's going to move even faster. So you are transferring energy from you by burning your chocolate cookies into the cart. Is that clear? Yes? Yes.
So kinetic energy and the force applied to a specific object are two different things.
Yeah, so force is Newton, energy is joules, which is Newton times meters. So again, if you write conservation of energy, one way to say that is that you have kinetic energy before, plus gravitational potential energy before, plus potential elastic before, plus your push, okay? Could be like applied force, or it could be fuel that you burn, okay? You add, like you have a booster, and it's already moving. The rocket is already moving, and you turn on the booster. So that will be energy that you put in the system. So it's going to go faster. It's like a booster with a space shuttle or with the rocket or SpaceX, right? You turn on your booster, you put more energy. So in, minus, you always have friction, air resistance taking away. And at the end, if you have a booster, it's going to move faster. So kinetic energy is going to move faster. And maybe you're going to have some gravitational potential energy because you went higher. And sometimes you have some problem with elastic potential energy. Yes.
Supply times the distance. Necessarily kinetic energy in a sense? Or no, it's work.
No, it's a form of energy. So it just means that this is your energy. It doesn't matter which form it is in. So you have potential energy, for example, you have gravitational potential energy of, if you are on the inclined plane, you have some kinetic energy because it's moving. So if you put a booster, turn on your booster, or if you are the booster, you're gonna add this, right? So if you are on top of the hill, maybe all that is going to turn into mostly potential energy, okay, because you are on top of your inclined plane, and into kinetic energy. So they have no problem switching in from one form to the other form. Is that clear? So you are at the bottom of your inclined plane, maybe midway, so you have potential energy, you are above the ground. It's already moving, it's already have kinetic energy. You turn on the booster, zoom. At the end, you're going to have kinetic energy left plus gravitational potential energy. So you can swing back and forth as long as you see it's conserved. Now, if you have friction, so if you have friction, that means that you're going to lose a little bit of friction. So this will go away. Okay, so that will be friction, and then it's going to lower the level of energy. Yes, right? Is that clear? So it's like a container, Bitcoin, dollars, doesn't matter. If no one is taking a commission, it doesn't matter. The total amount of money will be the same. Some will be in Bitcoin, some will be in dollars, some will be in Singapore dollars, some of it will be in euro, for example. Some will be in gold. Yes.
Let's say after the potential energy.
This one? Oh, elastic. Elastic after. So kinetic energy after, potential energy. I should put a prime. Gravitational potential energy after, elastic potential energy after. This is after. Okay? So I highly recommend that you take your book, right? So for example, you can shoot if you have an inclined plane and here you have a spring, why not? Okay, you can start with some kinetic energy, boom, boom, boom. And then at the end, it's going to be elastic and potential. But that's the way you're going to write it. Or you can do the net work equals the change in kinetic energy. Is that clear? What? Yeah. The work is force times distance. And that will be parallel. So the force parallel to displacement. So work is always force times displacement. Yes? Force times distance, right? Don't forget everything. Do everyone agree? The work done is how much energy is being transferred to transfer energy or to take energy away, a force has to be applied over a distance. If the force is perpendicular, there is no work done. Okay? Copy me? So that's why I have updated this slide here. Displacement. Displacement. Friction takes away, push, booster, put energy in the system. Is that clear? If it's not clear, think about money, and then it will be clear. Okay, I just want to also go back to this slide here that I have also updated because so many of you will go into engineering, so you really have to understand the meaning of average power. Average power will be the total work done on a system divided by the time elapsed. So it's the rate at which energy is consumed or energy is produced. So you can compare, for example, Ferrari or what's the beautiful car here? We see a lot of them, Lamborghini. Okay, so if you compare the power produced or consumed by a Ferrari to my Handy, I have a new Handy. Handy is about 200 horsepower. It's ridiculous. Compare that to a Ferrari, you multiply by 4. So it means the Ferrari will consume 4 times more energy for the same time. It has a very high metabolism. It works like us, right? If you have an athlete, they can consume 3,000 calories a day. It doesn't matter, everything is consumed. Like we have older people like me, 1,500 calories, it's still bad. Okay? So understand the meaning of power. It will be the total amount of energy consumed, produced per unit second. So average power, okay? Now you have a different way to do it, and that will be, that's what you're gonna need for the test, for example, but we already seen that. So if it's average power, you see, if the force is constant, so it means if you have a constant acceleration, so the force is constant, the work done is force times displacement. I don't have to say it again. Force times displacement. The force is parallel to the displacement, so you want to take the cosine, for example, and delta x over delta t, that will be the definition of the average velocity. Very good. So that will be a very convenient equation. I think it's part of your equation sheet. That's one useful equation that you will need for the test. Okay. Now, if the force is not constant, so that will be for our calculus component, since it's supposed to be calculus based. So you have, like, if you take a calculus class, you learn how to take the average of a function. How do we find an average of a function? You have to take the integral and you divide by the time elapsed. Okay, so that will be the definition of the average of a function. So that's what you did. So of course, instantaneous power, the instantaneous power, you see, delta W over delta T. Okay, you get a dot because we only want the force parallel to the displacement. That's why you have a cosine. So the general definition will be that. So it's not that hard, and it connects to calculus. Agree? Everyone? It's supposed to be calculus. We have to stretch it a little bit, okay? Stretch to the limits. Okay, so here, for example, very easy example, and you have two ways to do it. You can say the average power by definition is the net work over time. Agree? And remember, what does the kinetic theorem says? The network is equals to
The kinetic energy that was lost. So
Very good. Or gain.
yeah, the kinetic energy that was that the final kinetic energy minus the initial energy.
Thank you. Exactly. So by definition, the net work is the change in kinetic energy, gain or lost. So in that case, can we find the change in kinetic energy?
Yeah.
Yes, right? So you can do it very quickly. So way number one, it's easy. The net work is by definition the change. Do it, don't stare. Staring is not healthy. The change in kinetic energy, so that will be the net work. So that will be the change in kinetic energy. By definition, the net work equals the change in kinetic energy over, that's it. And then the average power is by definition the net work over the time. So that will be the change in kinetic energy over the time. So will be, so then you can do all kind of computation, right? So if you are in engineering, you work with robots, for example, so you can find the average power and what's your, sometimes they have race. So what's your chance of winning? So 0.5, the mass is 1000. Final speed is 27 square minus initial speed is 0. And then the time elapsed is 10. So 0.5, that will be 500 times 27 square over 10. Is that right? So it will be 50 times 27 square. So what do you get?
36,450 watts.
36,000 for
450 watts.
50?
Yeah, 450
watts, which is joules per second. So every second, it's going to consume, it's consuming. Okay, that's how powerful it is. Okay? So if we take two people, the same mass, and they go up to the third floor, but one is very quick and the other one is very slow, are they spending the same amount of energy? They have the same mass, so they have to do work. They go at a constant speed. They have to do work against gravity. What will be the work done when you go up? What will be your potential energy? mgh. Remember that the work done against gravity is always mgh, or the work, negative work done by gravity is mgh, always mgh. So if you have the same mass and the same height, are you going to to produce the same amount of energy? Yes. But what will be different? No, because you are moving at a constant speed. So if the time is different, the power, it will be the power. So the rate at which energy is produced. So that will be the difference between Ferrari and the Hyundai Venue. So you see, it's a metabolism. So we will spend the same amount of energy. Both students will use the same amount of energy, but one will spend it quicker, has higher metabolism. Okay. So way number 2, you can also say that will be the power. Okay, so that's a different notation. Okay, it's the same. It will be the power times the average speed. And how can I find the force, the net force? F equals ma. Okay, ma times the average speed. And what is the acceleration? Remember, we are reviewing for the final, right? You go from 0 to 27 in 10 seconds. So the acceleration will be 2.7, very good. 2.7 meter per second. So we have the mass, we have the 2.7, and remember that equation that I told you to memorize, the average speed, if the acceleration is constant, equals initial plus final divided by 2. Okay, so initial is 0 plus final is 27 divided by 2. And you will get, at the end, you're going to get the same answer. So that's a different way to do it if you are only using kinematics, right? Agree? So remember that, like, if something increases at a constant rate, so velocity time, you see it's increased at a constant rate, so that means the average will be just the midpoint, just there, right? Okay, so I wanted to make that clear. Okay, so let's look at something similar to maybe what you're gonna have. So you have a bike, and I'm gonna use work divided by the time. I want to use work divided by the time. No, I'm going to use the equation. I'm going to use the equation average power is force times speed. Okay, it doesn't have to be that, but I can use that. Okay, so it's interesting for everyday application. You going up a slope, which cannot happen here. Sadly, there is no slope around, which is very sad. 10%, so it's a 10% slope, and you want to know what's going to be the power, how much power you need from your muscles. So you have different way to do it. So don't wait for me, okay? Don't wait for me. So you have a slope, and it says 10%. So what does it mean, 10%? It means that for a run of 100, you have a rise of 10. So we can even find the tangent, okay, will be opposite over adjacent. Okay, so you can find alpha, which is what? It's a small angle. Do it. Don't fall asleep. 5.7. Is that right, everyone? Okay. So power. So you have different way to do it. So let's say you go up, and so you move at a constant velocity here, which is what's the velocity? 4 meters per second. So what are the forces acting on you? There is no friction. How come? Or we don't care if there is friction or not. The minimum power. So it means without friction. Let's say there is no friction. We don't care about friction, but what will be here? So you're gonna have to apply a force to go up, and you have to work against gravity. Very good. And gravity along is mg sine. Of course, you're going to have friction because otherwise you're going to go up. But they talk about the minimum that you need to fight against gravity. And then you will need more muscles, more muscular work because you have to fight against friction. So that will be the minimum. And let's say the distance is d. So let's say the work done by you, okay, on the bike will be the force. What is the force that you need to apply? Mg sine, yes? Yes? Times the distance, displacement. Okay, so average power by definition will be the by U, okay, that you have to produce will be the work, okay, divided by the time. So it's going to be mg sine over distance over time. And what's the distance over time by definition? The velocity. So mg sine times the velocity. And the velocity we have, it's 4 meters per second. Okay, so we get back to the equation. The average power, if you have a produced, delivered by you, it's you, delivered by you, and you have to fight against gravity. So that will be the power delivered by you through your muscles to the body. So that will be the average power will be force times velocity. And that's what we have here. This is the force that you have to provide against gravity. Again, agree? So that way, if you do engineering, mechanical engineering, that's going to be important to know how to compute that, right? If something is efficient, how much power you need, how much fuel you need per unit second. So that will be the mass, which is 80 times gravity, which is 10 times sine 5.7 times the speed, which is 4, and unit will be in watts. Okay? So since for those going especially into any questions, joules per second, it's a rate. How quickly energy is being delivered, burned, right? So it's a Ferrari against a Ford wagon or something like that. It's very slow and very boring. A Bentley, for example, is not boring. So as an exercise, especially if you are in mechanical engineering and you like car and things like this, you can do that exercise here without looking at the solution. I will let you doing it. And for cars, power is instead of being in watt, it's in horsepower. I told you that. That's because back then, during the Industrial Revolution, they tried to convince people to switch from horses to car. So to do that, they compare the power to a horsepower. So that's how they came to be with the horsepower. So horsepower is just a unit for power. Average car is 200 horsepower. Lamborghini is like 700 horsepower. So it's like 700 horses pulling the car. Okay, so this one you want to pay attention to it before the test. You see, it's an elevator. Okay, and it could be confusing because they ask you the power, but it's always power delivered by question mark. Okay, it's not the power taken away by gravity or by friction. They want you to find the power delivered by a force. So you can use the equation. Power will be the force you are interested in times the speed, for example. So when you are going up the slope, you are biking, that will be the power delivered by your muscles. So for example, here you have an elevator. It's acted upon by 3 forces. You have the lift, so that will be the tension here through the cables, and you have friction down, and you have gravity down. If it's moving at a constant speed, so we review, right? Up equals down, and you can find the tension. Do you agree? Do you agree? Right? Up equals down, speed is constant, or it's at rest. Once you have done that, then you can use average power equals force times speed, and you can find how much power is being delivered by the lift from the elevator. right? So that's why they have a maximum weight, because if there is too much weight, maybe you're gonna break the cables or something bad can happen. I'm very scared of elevator. I'm always scared. I've seen too many movies, horror movies when you fall. And once you have that, then you can convert to horsepower. And inside textbooks, you do have that thing called a textbook. You're supposed to open it, hide the solution, and work especially if you're an engineer, right? If you want to go to engineering, you want to do it now. Don't wait. Do it now. Practice now. Yeah, and that's just showing you that theorem, kinetic work theorem. If you massage it a little bit, you get conservation of energy. So total mechanical energy before equals total mechanical energy after, if you don't put something in or if you don't remove something. Okay? Okay, so let's start a new unit. So any questions? So don't forget test number 3. Okay, I hinted today. So inclined plane, the elevator. Test number 3 is not going to be hard, except I took a picture of the question, so you cannot copy and paste. So linear momentum, I'm going to introduce a new physical quantity. That physical quantity is called the momentum. So Newton called that the quantity of motion, and it will be the mass in kilograms times the velocity. And you see it's a vector. Okay, it's a vector. So you take a vector here, you multiply by the scalar. So that's going to be a vector, right? And a way to think about it, you can think of momentum, how much punch can be delivered by a force, right? How much punch. So for example, if you do boxing, they have something called the cross, right? So that means that you're going to deliver the most momentum because you throw all your weight into that cross, right? So that will be the power punch. I highly recommend boxing if you're upset at something, upset at your physics professor with that weird French accent. Do boxing and then everything goes very well. You just have to be very careful. It's a good therapy. So anyway, momentum is the mass times the velocity. Okay, so the first thing, we're going to talk a lot about the change in momentum, right? So momentum is going to be the mass times the velocity. So it's a vector, so it's going to have components. So this one will be a kilogram. This is in meter per second. The unit for momentum will be kilogram meter per second. Is that clear? So the thing that we're going to use is the change in momentum, which is always change the final momentum minus the initial momentum, okay, which is the mass, the final velocity minus the initial velocity. Okay, so I'm going to forget about the vector thing because we're going to work in one dimension for now, but it will be the mass. You factor out the mass, so it will be the final velocity minus initial velocity. And be careful, velocity can be negative. So that will be the mass times the change in velocity. So the change in momentum equals to the mass times the change in velocity. Okay? Now let's look at Newton's second law. So Newton, we always say F equals ma. Okay, so if there is a net force, there is an acceleration. The acceleration is the force per unit mass. But that's not how Newton, when he wrote his book, Principia, he didn't say F equals ma. He said, so force equals mass. What is the acceleration?
Delta V over delta T.
Exactly, thank you. Delta V over delta T. Again, it's a vector. So I'm not doing the derivative, so I'm just doing this way. It's easier. So you multiply by the time elapsed on both sides. So you can have force delta T equals m delta V. So again, this is a vector, this is a scalar, this is a scalar. And what is that quantity? M delta V? It's going to be delta P, the change in momentum. This is big here, delta P. So what does it mean? It means if you apply a force over a distance, there will be a change in momentum. So if you apply a force on the system during a time t, there will be a change in momentum. Or if there is a change in momentum, there will be a force over time. So boxing, if you punch, there is a change in momentum, you're going to apply a force. Does that make sense? Over time. And of course, shorter the time is, for the same change in momentum, so you go from here to boom, right? So the change in momentum will be the force will be the same. Okay, let's say you cannot punch harder than that. Shorter is the time, larger is the force. So it's always a trade-off between force and time. Likewise, you can think of that as a trade-off between distance and force. So if you do the cross, large distance, small force equals to small distance. What did I say? Small force, large distance equals small distance, large force. That's why it's so bad. So that will be the change in momentum. This here, we're going to introduce a new physical quantity, and we call that the impulse. Impulse, so it depends on the textbook. So sometimes notation is I, uppercase I, or sometimes it's going to be J. So it's a new physical quantity. You can always check your equation sheet, as we go along. Impulse, Newton, 1 second. So what's the impulse? You can think of that as a way to measure the punch of the force. So if there is an impulse, there will be a change in momentum. Or if there is a change in momentum, there will be a punch delivered by the force, right? So that's a new physical quantity. It's called the impulse. The unit is Newton second, and it's a vector. So it's the punch of a force. So this is in and keep here, Newton. He didn't know about kinetic energy, but he introduced, this is his second law. That's the way he did that, second law. And he also invented calculus just for the sake of developing his laws. So you see, momentum has components, has the x component, y component, z component. It's a vector. So here you have it. The net force is the change in momentum over time. So if there is a change in momentum, there will be a force delivered, and it depends on the time. So we define the impulse. So here they say capital I. So I don't know, in the book, sometimes it's J. It depends on the notation. That will be the impulse. Unit is Newton second. Okay? So if there is an impulse punch delivered to a system, there will be a change in momentum. If there is a change in momentum, there will be a punch, a kick. So very easy here. So for example, let's take an example when you are playing tennis, right? And you are not under any non-legit stuff, so you cannot increase your muscles, right? So there is so much force that you can apply over a time t. So the force you cannot change, but you want to tennis ball to go as fast as you want, as fast as you can, so it make it harder for your partner. How can you do that? Do you just do bing, or do you follow through? when you catch the tennis ball, do you just do, or you follow through? Follow through, thank you. Baseball, right? I don't understand baseball, but I just understand that part. When you catch the ball, you have to follow through. Why? Because you cannot increase the force. There is so much force here. However, for the same change in momentum, for the same force, right? Sorry, for the same force, you can increase the time during which you are applying the force. So you are following through, and you are increasing the momentum. So if you increase the momentum, the tennis ball will go faster, and of course it will make it harder for your partner. Does it make sense? So you cannot change the force because there is so much muscles that you have. So you increase the time. Does it make sense? Isn't that cool? Right? So you follow through. So you increase the time during which the force is applied, right? You increase the time. And so let's do this one. Very, very, very super easy, extra, super easy. Extra, super easy. Easy, super extra. Do. Don't stare. Don't you? Okay, so what is the equation? Apply a force during a time t, and the momentum will change. So that's the change in momentum. That's going to be the impulse, which is the punch delivered by the force. Okay, so you're going to follow through, meaning you cannot increase your force. It is what it is, but you can increase the time to increase the momentum. So the force times the time. So it's a contact time. So 0.005. So 1, 2, 3 equals the mass 0.06. Change in velocity will be the final, so 40 minus initial. So that's going to be, yes, very good. What's your name again? No. Huh? No. Okay. Exactly, 480 Newton. And you divide by 5 to get in pounds. So then you tell me if it makes sense or no. Does it make sense, that much pounds? Yes? Okay, so that will be in Newton. Is that clear? It's easy, right? So you have to follow through. You follow through, so increase the time. The force is the same, so the momentum will go up. So the idea is this way. So the force, you cannot change your muscle. It is what it is. But if you increase here, it's like you tune. Okay, so if you increase this one, this quantity here will increase. This one stays the same. It's the mass that will be the force. So increase here, increase there. Okay? So in reality, the force is not a constant, right? So if you, for example, if you hit something, the force first is going to be 0, and then it's going to increase, and then it's going to decrease again. So it's going to increase, decrease again. But we can show, that will be calculus, that everything happens like you have an average force, right? So if you use this here, you have to do an integral, but that will be the same thing as average force. So that means if the force is not constant, then you use this equation here, and instead of having a force here, which stays the same, you take the average force. Okay? because so force, average force, okay, times the time equals the impulse. So that will be the punch. So what exactly is a force? Average force, an average function in calculus. Okay, it will be the integral from 0 to whatever t here of a force that will change with time dt over 1 over delta t. Okay, so that's what you are supposed to do to find the integral here under that curve. So that will be the real definition. And then you multiply by delta t equals j. So in your book, the impulse will be defined as the integral from 0 to a or f delta t. So that will be the real definition of your impulse. You see, you have to integrate. Okay, so the definition of impulse, you don't have to understand, it's just a definition. What's the definition of impulse in physics as defined by Newton, as understood by Newton? The impulse, what is the impulse? It's the punch delivered by a force, is that integral here, that integral there. Okay, by definition, if I go to the real definition, if you go to your textbook that you are supposed to do, the punch delivered by a force will be a force that will change with time, will be this area. And then with the help of very simple calculus, we find that this area will be the same as that area. Okay? It's very simple calculus. Calculus should be understood for physics because after all, who invented? If you learn calculus without physics, it's like you memorize and then you forget. Okay? You see? It's bouncing off, so there will be an impulse, okay, that is making the ball bouncing off. See, the force increases and then it decreases, and that area in yellow will be the same as this area there. Okay, it's calculus based, so you should enjoy having a little bit of calculus. It's nothing bad, it's a simple integral. And what is an integral? It's the area. Very good, area under the curve. And that's how it was defined by Newton. Okay, he understood that the punch delivered by a force, and if you do boxing, you will understand what I mean, equals this area under the curve. Okay, so this is called the impulse momentum theorem, right? And it says that the net force, okay, so the sum of all the forces, it has to be average. So the net force average times the time equals the change in momentum. This is called the impulse momentum theorem. So it means if there is a force over a time, the momentum will change. If there is a change in momentum, there will be a force. And I think I've already show you this one. Okay, so you have you have momentum, right? It's going to move faster and faster and faster. Before it's going to reach the tree, it has a huge amount of momentum. Not only does it have speed, but also mass. Momentum is mass and speed. All that momentum will be translated as a force over time. If the time is small, the force is huge. I hope they didn't do it on purpose. I hope it's an accident, because that's not nice.
Hit the tree.
So momentum is force.
Yeah.
Right? Okay, only boys will do things like that. But it's a stereotype. Okay, I hope I didn't offend it. anyone. But you see, the impulse equals the change in momentum. Okay, so this drawing, actually, you see, I don't know if you watched Mike Tyson. Did you? It's a fake. I believe he was faking it. Don't you think so? Right? Because if you watch him training, he was like moving everywhere. He's super good, and all of a sudden he doesn't move. So maybe I should cut that. I should edit the video, but I think it's not possible. So anyway, so this drawing comes from the book, very, very nice book I told you about. It's called Conceptual Physics by Paul Hewitt. And before going back to physics, because his teacher said you are good to nothing, you should go into art, whatever, you should not go to college. So before going back to college, he went to boxing, he went collecting uranium. He did many things. So and he's very good at drawing. So here is the story. If you are punched, so for a given change in momentum, so you are punched like this, a jab, boom. Do you just stay stiff or do you roll over? Roll over. Why is that? Because for the same change in momentum, the box glove, okay, is moving fast and then stop to your face. Okay, so the same change in momentum, if you increase the time of impact, what's going to happen to the force? It's going to decrease. Increase the time of impact, decrease the force of impact. So typical conceptual questions. So that's why if you have an airbag, right, crash, you increase the time of impact, you decrease the force. So they learn to roll over. Okay, you have to roll over, otherwise you're gonna break your teeth or whatever. Okay. So that's why to write the equation, Newton's second equation this way makes more sense. Same thing here. Do you rather crash in a stack of hay or in a stack of in the wall? Hay, right? Because you increase the time, you decrease the force for the same change in momentum because you stop from moving. Obviously, when you jump, do you bend your knees or you stay stiff? Bend your knees, same reason. The change in momentum will be the same. You stop that gravity, you fall and gravity will stop you. By increasing the time of impact, you're going to decrease the force, right? So this is a typical mistake by students. Is it harder to stop something or to make it bounce? So do you think it's harder to stop or to make it bounce? So you can do the experiment. I used to do that, but here it's not very convenient. Someone is on a chair with wheels, right? And you shot a person to another person. So is it harder to stop the chair or to stop it and reverse the motion? Very good. Stop and reverse. So bouncing means more change in momentum, means more impulse. So that's why when people who are players football, if you just stop versus stop and bounce, it's always worse if you bounce because you need twice the force. So let's show that. Let's just take a very simple example. You have two objects. So let's say they have the same mass. Let's say it's 1 kilogram, just to make it easy. Let's say the speed is 2 meters per second. So it's stop for this one and this one bounce off with the same speed. So it means there is no loss in energy. Can you find the change in momentum for both cases? Which is the impulse. Okay? Let's prove it. So let's say you have 1 kilogram here, you have 1 kilogram here. So it will be always students making that mistakes. Even though I insist, It doesn't matter. I will always get the same mistake. So I don't know, I can take plus this way, minus down. So the only challenge in this unit is to remember that momentum is a vector. It has the same direction as the velocity because P equals mv. Okay, so do the computation. So it's coming back here, magnitude is 2 meters per second. Find the change in momentum for the teddy bear and the change in momentum for bouncing ball. Do it! Don't stare. Do it, do it, do it. So number 1 and number 2. Okay, so what is the change in momentum? It's the final momentum minus initial momentum. So the change in momentum is m v final minus v initial. But be careful, velocity can be positive or negative because it's a vector. So for the teddy bear, so the change in momentum will be the mass is 1 kilogram. So not just 1, so it's just 1. Agree? 1. What will be the final velocity? 0 minus, what is the initial velocity? 2. So the impulse, so the punch, yeah, has to be delivered will be minus 2 Newton per second. So here, just to show you what is killing. It's not the fall, it's the landing. To stop it from moving, you need to apply a impulse. And that impulse will be provided by the normal force. Okay, so he will be acted upon by the normal force and the weight, but the normal force will be larger than the weight because you have to make it go slower. It's the normal force that is the killer. It's not the fall. But let's look for the ball. So the change in momentum will be, so what's the final velocity here? So I did a mistake. So down is plus. I'm going to take down to plus and up to minus because I said this was plus. So I'm going to say to be consistent, down is plus and up is minus. So what's the initial final velocity? Negative 2. Very good. Minus, what's the initial velocity? 2. So what's going to be the impulse? Very good. So you need twice the force because not only you have to stop it from moving, but you have to reverse the motion. So when you have two footballers and they collide with each other, and let's say you have the big one winning, right? So it's push the skinny one is going to move this way and then it bounces back. For the brain, it's going to be very bad. The worst thing that can happen to your brain, it's moving and then you force it to stop and you force it to reverse. So your brain in the skull is bouncing up. That's worse. It will be twice the impulse, twice the bruise. You don't want to have too many bruises. That will be bad at the end. Okay, so let's do this one quickly. It says nip out. Okay, number slide 17. Zoom. So it's bouncing up. The mass is 1500. Okay, so we have to decide. Let's say now I take, I don't know, it doesn't matter which way is plus, which way is minus, but you have to stick to it. So the change in momentum equals the mass, which is 1500. Do it, okay? But what's the final velocity? The final velocity is very good. Minus, but what's the initial? Negative 15. And here they are very nice because they put negative 15. Usually you make a left, an arrow to the left with the magnitude on top, but they don't tell you it's negative. You have to understand that it's going to be negative. So the change in momentum will be 1500 times 17.6. Okay, so the change in momentum will be, you do it, don't stare. More you do, less you have to worry about the final, right? So 26,400, that will be for the final. So you can say kilogram meter per second, or you can say this is also equals to the impulse. So it doesn't matter, both units are correct. So that will be the impulse, so the punch delivered by the wall. So it's the wall. You push on the wall is pushing back on you. So that will be impulse. The impulse from the wall, the punch delivered by the wall on the car, because you cannot push without being pushed back. So that will make you bounce off. Okay? Isn't that interesting? Because this is like everyday experience, so it's super interesting. So the average force, so we have average force times time equals impulse. The force, that's what we want. And you see that smaller is the time, worse it gets. For the same change in momentum, if you decrease the time of impact, you're going to increase the force. So the average force will be, so you divide by 0.15, which is 176,000 Newton. It's a huge, so you divide by 5 and you get in pounds. That's very bad. Okay?
US.
Newton. That's the unit for impulse, the same thing. Agree? Yes. So if you work in a circus, and if it's cement here, of course, you're gonna be like in parts. But if instead you have a net, then of course it's much better, because you're gonna stop from moving at the end when you fall. But if you increase the time of impact, if you increase the time of impact, you decrease the force. So that's why falling on cement is worse than falling on grass, for example, because there is no yield. Yield means more time, right? Yeah. Let's see here. Okay. What do you think here? Quickly. So you go from super, so it's bouncing off. So the thing that you can remember, you can memorize. When something bounces off, you add initial speed and final speed. When it's bouncing off. So when you're going to find a change in velocity, it's not going to be 0, it's going to be 20, exactly. Okay, so it will be 20, and then the mass in kilograms will be 0.1. So 20 times 0.1, it's going to be 2. And then I give that for the final, and half of the students will tell me it's 0, because they do 10 minus 10. No. Because you have to stop it and reverse the motion. So it takes force. It's not zero force. Now, if you want to find the force, you will say the change in momentum is 2 and the time is 0.1. So 2 divided by 0.1 will be 20. Very good. Which is divided by 4 pounds. So again, it's the landing. Okay, so that's interesting. Super interesting. So you know there was the gold rush, like all the cowboys movie and everything, going west. And some people don't know that, but the people who made the money at the time were not the gold miners, right? Because first of all, the first people digging for gold, okay, it was easy for them. Gold was there. Okay, they became rich. But most of them, they had to work so hard to get a tiny bit of gold, and then they will spend their money going to the bar or whatever, right? Or to buy hardware. So the people who made their money, so we call that the old California money. The people who made the money were what? The people who were exactly selling the shovels. And Stanford University, okay, was founded by Stanford, who made his money selling shovels. So when there is an economy boom, you want to support the economy, but you don't want to be in the economy. So, for example, when you had a boom for Bitcoin, okay, you want to sell the hardware, all those graphic cards and the video game like a computer. That's how you're going to make the money. Because by mining, okay, at the beginning you're going to make money and then it's not going to be as good. So same thing for the gold rush. Okay, so the people who made their money were the people who, like Lewis, for example. Lewis is a very good example. He made the jeans, right? That's how he made this money. Because the people, when they work very hard in the field, they don't want to buy a new pants every day. So those jeans were wonderful. They were made for them. That's how he made his money. So likewise, you have this guy, Felton, and he had the idea. So those gold miners, like people digging for gold and digging the ground, they had to use water mill for different. The water mill at the time were like a motor, right? So you will use water to power like a device, like to sow woods, for example, right? Or to wash the gold, or to take the water out of the ground. And he got the idea to patent a new paddle. So you see, instead of having to used to be the paddle were flat, he made the paddles curve. Why? Because if it's bouncing off, you're going to provide more impulse, more punch. So the wheel will go faster, right? And he patented his wheel. So it's a very, very, very good example how people actually made their money at the time. So it was not the gold, never been the gold. It was the people uh, selling the hardwares. So here, you see, even if you go, like, if you go to the open, so for example, if you go to Smokies Mountain, the Smokies, it used to be that they were like, even if you go to the Appalachian, the big business back then was to woods, right? To cut the woods to as a fuel, right? So that all the forests were almost gone. By the way, it's a good thing that they found fossil fuel, because if it didn't have found fossil fuel, we will not have any forest left, because they were cutting the forest as crazy. So you had the sawmill, and how did they power the sow was with a water mill. And if you visit like the Smokies, like they kept the old mills and they kept the old houses that people used to have, and you can see how it was working because you have so many water, like river, right? Like all those river flowing, they will power the wheel and it will cut the woods, right? So if you go to the White Mountains in New Hampshire, and I think New Hampshire, you have the old, you can visit them, right? So it's a good thing that they found fossil fuel, otherwise there will be no forest left. And if you hike like in the Smokies, you see that all those trees are quite young. They just reborn trees. So anyway, that's just a parenthesis. Isn't that interesting? Right? Okay, so then we go to conservation of momentum. So you have conservation of energy, conservation of mass, conservation of electric charge, conservation of speed, and you have conservation of momentum. But this one is very easy to understand. For every force, every action, you have an equal and opposite reaction. You cannot punch without being punched, and you cannot punch harder than you are punching. So in that case, you see, it's a famous scene in Mowgli, which is my favorite cartoon. You see, my watch stopped. It's not. It just stopped. So the force here will be the same, and even though Baloo does not want to punch him, he will still be punched. So if he's punching Baloo with 1 pound, he's going to be punched with 1 pound. The force is the same, but not the consequence. Okay, because F equals ma. For a small mass, obviously it doesn't have any fat. You need to go keto. It will have a huge acceleration. This one has a huge mass and a small acceleration. So if you you multiply the time, both sides, you're gonna get the change in momentum for Mowgli will be equals to the change in momentum for Baloo. So that comes from every action you have an equal and opposite reaction. Do you have the